Yeah, hello everyone. Myself Maruti, welcoming you all to this physics video session. Right. In this video, I'm going to explain you regarding quantum mechanic model. Of course, one of the best quantum number in that is nothing but principal quantum number. Of course, we are having many more. I'll be discussing all those in this video. Right. So what's a quantum number actually? Right. Quantum number is nothing but after Mr. Niels Bohr and Mr. Sommerfeld has described the structure of the atom. Of course, they made some wrong assumptions, but those assumptions were rectified by Mr. Quantum. Erwin Schrödinger, and he has proposed quantum mechanical model. Okay, so I am going to discuss regarding that one. So the topic is mechanical quantum number. Right, what's a quantum number actually? Right, what does he mean? So what does he mean means suppose if you are having nucleus at the center of the atom. Suppose we take this as the nucleus. Right, so here where the chance of existing the electron is, where the probability of finding the electron, where there is much chance of finding an electron, the region, the space, that's what. If you consider this as the nucleus, this is the space around the nucleus. I'm not defining any shape for that one. So here, probably here, right, at particular time, electron may be present in this region. Right, electron may be present here. There is much chance of existing. Right, that's what he says. Right, the maximum probability of finding the electron around the nucleus and their energies also is indicated by quantum numbers. That's what. Of course, not only the region where it is, we may talk about the state in which it is. State. In which state, right? Electron state, what we can call it as. Electron state means in which direction it is moving, right? Right. In which direction? Is it rotating in the clockwise? Is it rotating in the clockwise or anti-clockwise? In which direction it is rotating? We can check it out. Is it in the clockwise or anti-clockwise? Where it is present, that is maximum probability, and also towards which axis it is oriented. Right, oriented. If you take, right, this is nothing but the x-axis, this is nothing but the y-axis, and this is nothing but the z-axis. Right, these quantum numbers explains us to which axis the electron is oriented itself. Right, is it along the x-axis, or is it along the y-axis, or is it along the z-axis? In which direction? That's what he says. If the direction we are talking about the orientation, we are talking about where it is present, how it is present. All these things can be known or can be described with the help of quantum numbers. That is what he says. Maximum probability of finding the electron, of course their state, the position around the nucleus, and their energies also. Basing upon the position in where the electron is, we can estimate the energy. If it is nearby, it may have some energy. If it is far away from the nucleus, it may lose the hold of the nucleus from the electron as it is far away. All these things can be known with the help of quantum numbers. That is what. Now, what are these quantum numbers? Of course, we are having 4 quantum numbers. Principal quantum number denoted by N, azimuthal quantum number, magnetic quantum number, and also spin quantum number. Now I like to start in a brief regarding every quantum number. So the first one what I have chosen is nothing but principal quantum number. Right, this quantum number will be telling us about the size of the orbit and the energy of the orbit. That's what he says. Size and energy of the main shell, main shell is nothing but the orbit, is described by principal quantum number. This is the first important point what we are supposed to remember. Size and also the energy. What is the size? That's what I said. Now let me come back to this one. Suppose if you take the nucleus here, right, This is the first orbit I am talking about, and this is the second orbit I am talking about. Right. If the electron is somewhere here, what about the energy? In the same way, if the electron is somewhere here, what about the energy? That is what he said. Size and energy of the main shell. Right. Right. So here, right, energy is E1. Right. Here I am taking it as energy is E2. Right. Means in the same way, the next orbit will be having something like energy E3. Right, and we know the orbit may be having more energy. This might be the excited state, this might be the ground state. Right, so that's what, if you know the principal quantum number of the orbit, we can say what is the size of the orbit and also the energy of the orbit. That's what we say. This is the main point what we have to remember. Size and energy of the orbit or the main shell can be known with the help of principal quantum number. That is what size and energy of the main shell is described by or is given by or indicated by principal quantum number. That's what he said. If it is nearby, if the orbit is nearby to the nucleus, it may have different energy. If the orbit is away from the nucleus, it may have different energy. If you know the principal quantum number, right, we can know how much energy is there in the orbit. In the same way, what is the size? Is it close? Is it small? Is it a bit larger, the orbit? This is the bigger orbit than this one. So that's what. So size and energy of the main is described by principal quantum. This is the main point what you have to remember. Now the second one, who has proposed this principal quantum number? We are supposed to remember it's nothing but our great Niels Bohr. Niels Bohr has proposed the principal quantum number. The point one. Now let's come back to this one. What is the symbol of this principal quantum number? Principal quantum number is symbolized with the letter small n, denoted by small n. Let me come back to this one. Suppose if I take the same orbit, first orbit and the second orbit, we know, let me take the example of these two orbits here. This I like to take it as excited state. Let me take the electron. Suppose an electron is present here, right here, and I like to take it as excited state. Right, and here the orbit, right, let me take this one as ground state. Ground state. Okay, now as we all know, when an electron jumps from higher orbit to the lower orbit, it loses energy. When an electron jumps from higher orbit to lower orbit, it loses energy. Now let that energy come out. Right, is emitted out in the form of electromagnetic radiation. Right, electromagnetic radiation if it is coming out. Now if we take that in that emission spectrum, if you check it out in the emission spectrum, now we'll be able to see, right, these are the lines what we are able to see. These we call it as a line spectrum. Okay, now what does I mean? Right, here let us assume, right, what I am saying, when an electron jumps from higher energy orbit to lower energy orbit, it emits energy in the form of electromagnetic radiation. Right, if we see that electromagnetic radiation in the emission spectrum, how it look like? It looks like a line spectrum. What I want to say is each line indicates one orbit here. Each line indicates one orbit. Let me take an example. Let me take the first one as K. The first orbit I like to take as K. Now the second orbit I like to take it as L. This is nothing but L. Now the third orbit I like to take it as M. This is nothing but M. Okay, now we are talking about the principal quantum number denoted by N. Now what I want to say is the principal quantum number of the K shell will be taken as N is equal to 1. Right, principal quantum number of L is n is equal to 2 and n is equal to 3. These are the principal quantum. That's what I mean, right? It is symbolized by n, and the next point, it is taking all positive integer value. So for the k shell, we take n is equal to 1, n is equal to 1. For L shell, we take n is equal to 2. For M shell, n is equal to 3. What does it mean? What does it mean? Means for every orbit, one principal quantum number is there. Means for every value of principal quantum number, it relates with one orbit. If you take n is equal to 1, it relates to k orbit. K. For n is equal to 2, it relates with the L. If n is equal to 3, it is nothing but m. So what does it mean? Means it is symbolized with n. It is taking all positive integers. And also, for every orbit, there is a definite principal quantum number. What's the value of principal quantum number of k? N is equal to 1. In the same way, and so on. That is what he says. Every n value is related to one fixed orbit, discrete value we are having for every orbit. Now, let's come back to the main thing. Number of orbitals in an orbit is given by n square. Principal quantum number is helping us in all the way. Right. It is giving a fixed value for every orbit, and it is also giving one important information for us. That is nothing but how many number of orbitals are present in every orbit. How many number of orbitals? It is given by the formula n square. N square. Let me explain to you this. Right. So here k. Right. What's the n value of that? It's 1. Right. How many orbitals are there? We are talking about orbitals. Right. We are talking about orbitals. Now k orbit is having only 1. So what is 1 square? N square is nothing but 1 square is nothing but 1 here. Means for first orbit, how many orbitals are there? If what is the value of n? 1. How many orbitals it is having? 1 square is nothing but 1. Right? In the same way, for the second orbit, now let us take the second orbit. Let me take, this is a k, right? And this is L. Now let me clearly explain you. L orbit has one s orbital, right? L means nothing but a 2s. Okay, right? In the same way, we'll be having 3 orbitals, right? This is nothing but a 2px, this is 2py and 2pz. Now, if you count the figure, this is one orbital, this is the second, third, fourth. So that is what the point says, right? So for n is equal to 2, which is nothing but KL, L is nothing but n is equal, for L, n is equal to 2. How many orbitals we are able to see? 1, 2, 3, 4. That is nothing but n square. N square is nothing but 4. Why? Because n is equal to 2. Alright. So what does it mean? What does it mean? Means for L, we are having one s orbital. Yes. And how many p orbitals? We are having 3. So 1, 2 and 3. Totally, we are having 4. Right. In the same way, if you like to know how many in the third orbit, which is nothing but m, if you like to know how many orbitals it has, straight away, what is n is equal to? We talk about the last point here, a maximum number of electrons in an orbit. So the maximum number of electrons in an orbit is given by principal quantum number, and the formula is 2n square. You have to remember, maximum number of electrons in an orbit is given by the formula 2n square. Let me talk to you regarding that. Now, if you take k orbit, right, what's the n value there? N is equal to 1. If you like to know what the number of electrons present is, the formula given is 2n square, which is nothing but 2 bracket square. What's the n value of k? 1. So which is nothing but 1 square 1, it's nothing but 2. Right. How many number of electrons are present in the first orbit? 2. What are there? So in the first, we'll be having s, so this is nothing but 1s, and it will be having 2 electrons. Now, that's very simple. Now, let's go for KL value. N is equal to 2. Right? The formula is 2 2 square, it's nothing but 2 square is 4, 4 2 is 8. Where are these two? As you all know, just now I have said to you, in the 2s, we'll be having 2 electrons. And as I said, this is nothing but 2px, this is 2py, and this is 2pz. And in each orbital, we'll be having 2 electrons. And if you count it, 1, 2, 3, 4, 5, 6, 7, 8, 8. In the same way, if you go for m, it's nothing but a 3, and the formula is 2, 3 square, 3 square 9, it is nothing but 18. If you check it out, in the 3s, we are having 2 electrons, right? Here we are having 2, 2, and 2, and all together here, if you count the number of electrons everywhere, 10, 16 plus 2, totally 18 electrons are there. So that's a clear explanation that the number of electrons present in single orbit is given by the formula 2n. Now let's talk about the relation of principal quantum number with other factors like size of the orbit, energy of the orbit, and also the distance of the electron from the nucleus. I repeat, let's talk about the relation of principal quantum number with size of the orbit, energy of the orbit, and distance of the electron from the nucleus. Now let's go for that. Right, n's relation with the size of the orbit. N is directly proportional to the size of the orbit. Means as the smaller the n value, smaller the size of the orbit. In the same way, larger the n value, larger the size of the orbit. That's what we mean. Principal quantum number is directly proportional to the size of the orbit. Now let's get back to the figure. Here, what's the n value here? For k, we are having 3 orbits, k, l, and m. For k orbit, n is equal to 1. For l orbit, n is equal to 2. For m, n is equal to 3. As the principal quantum number is increasing, if you check it out, the size of the orbit is also increasing. As the principal quantum number, n is equal to 1, size of the orbit is smaller. Right, n is equal to 3, the size of the orbit has increased, right? So principal quantum number is directly proportional to the size of the orbit. Point 1. The next one, n's relation with energy of the orbit. So how is the relation of the energy with the principal quantum number? Again the same relation. N is directly proportional to the energy of the orbit. Means if n value increases, energy of the orbit also increases. If n value decreases, energy of the orbit also decreases. Now let's get back to the example here. We know, right, let's call the energy of the first orbit, n is equal to 1 is E1. In the same way, n is equal to 2 as E2, and n is equal to 3 is nothing but E3. So it's already clearly known the orbit which is E3 is in the excited state, or it is having more energy than the orbits which are close to the nucleus. So as the n value increases, energy of the orbit also increases. As n value decreases, energy of the orbit also decreases. Now let's come back to the third relation, that is n's relation with the distance of electron from the nucleus. Now if you talk about the same thing, now if n value is equal to 1, for k, the electron, the distance from the nucleus to the electron is less here. Why? Because the principal quantum number is less here. Alright? In the same way, if the principal quantum number increases for the third orbit, now the distance of the electron from the nucleus has increased. As the principal quantum number increased, the distance of the electron from the nucleus is also increased. So this is how principal quantum number helps us to know lot of things. So that's what principal quantum number is, one of the main factors explaining about the electron, its position and its state. In this channel, I have been placing both math and science videos.